everyone. So welcome to part 3 of chapter 7. Today we're going to be continuing where we picked up last time when we talked about, we were talking about the Bohr model, and we talked about, how where electrons are in the atom, and we talked a little bit about the uncertainty principle and things like that. And so today we're going to combine all of these topics that we've talked about thus far and talk about the quantum mechanical model of the atom, which is the most current and up-to-date model of the atom. It's actually not the model that we're going to use to talk about electrons when we get there in this next chapter, in chapter 8. But we do, and the reason that we're not going to use the quantum mechanical model in chapter 8 is because it's pretty tricky to understand. You need some quantum physics and some Calc 3. And the Bohr model gets us pretty close to the right answer. Like we said last time, the Bohr model only works for hydrogen, but it's actually pretty close for a lot of the other elements. It's just not quite right. So today we're going to talk about the quantum mechanical model, talk about shapes of orbitals and things like that. And then just kind of for your reference, so this will be, if you're looking at the PowerPoint, this is slides 52 to 69 in the PowerPoint. So the third portion of the PowerPoint. We're going to finish chapter 7 today, and this will correspond to chapter 7 lecture worksheet pages 3 and 4. And then after you finish all the lecture worksheets, I would go through and work on the study guide. The study guide has more problems that will help you out. This particular lecture worksheet is only 4 pages long, so you don't have a ton of practice problems. And so, like I said, I would go through and do the ones on the study guide as well. You do have an ALEX assignment due on this on March 25th. So you have 2 different ALEX assignments for chapter 7. One of them is due on March 21st, and the other one's due on March 25th, and then that will kind of take care of chapter 7. So make sure you're paying attention to those dates. And yeah, as always, send me any questions as you have them. So we are going to talk today about wave functions a little bit. So quantum mechanics, which is also sometimes called wave mechanics, is the treatment of atomic structure through wave-like properties of the electron. Okay, and we talked last time when we were talking about that, the Heisenberg uncertainty principle, and the de Broglie wavelength, right? That particles, any particle, actually has some wave-like properties. And when we're looking at the electron, because the electron is so small, those wave-like properties matter. Right? Whereas we were talking about a baseball last time, baseballs are very large in mass, and so their wave-like properties don't really come into play. But for things really small like the electron, it matters that electrons also behave like waves, kind of like light, right? We know that light can behave as both a particle and a wave, and so can electrons, and realistically, so can anything else. But because electrons are small, this matters. So Erwin Schrödinger, right, and maybe you've heard of Schrödinger, especially, like I said earlier, if you watch The Big Bang Theory, he developed an equation to describe the hydrogen atom. So if you'll recall, Bohr was working on the Bohr model, right, which described where the electrons are the one electron in a hydrogen, and we said that the Bohr model worked great, but it only worked for hydrogen. So Erwin Schrödinger kind of took that, and he's like, okay, I'm going to find a way to describe what's happening in hydrogen, but I'm going to also make sure that it applies to, the other elements, not just hydrogen. So wave mechanics provides a probability of where the electron will be in a certain region of the atom. Okay, like we talked about last time, the better, right, the Heisenberg uncertainty principle, the better we know where an electron is, the less we know about its velocity and where it's going from there. So this is just a probability. It's like the electron will probably be there. It might not be, right, because it's zooming around doing all kinds of things, but it's probably going to be in that area. And this is about a 90% chance, right? So there's a chance the electron will be somewhere else. So the Born interpretation is that the square of the wave function. So this one up here, the probability, right? If we or the wave function itself, sorry, if we square the wave function, which is this, it gives the probability of finding an electron in a small volume of space around the atom. Again, we're not going to get into too much with the calculations for this because once you get into this mess, then you now need to have already finished Calc 3 to be able to solve these particular integrals. So we're not going to mess with that. But I do want you to know that when you see that symbol, that means the probability of finding an electron in a small volume of space around the atom. And so this interpretation, right, this probability of finding the electron leads us to the idea of electron cloud density, right? This electron density rather than a discrete location. So like the Bohr model, right? The Bohr model said, okay, here's our nucleus, and the electron is going to be either here or here or here, right? But this is different from the Schrodinger equation and the Schrodinger model, the quantum mechanical model. This now talks about areas where the electron might be found. So rather than saying it's going to be on this ring, we're saying, okay, instead, it's going to be somewhere in here, somewhere. Okay, that's kind of the difference between the Bohr model and the quantum mechanical model. So the quantum mechanical model, right, treats the electrons as waves rather than the Bohr model treated them as particles, right? And so this was the reason that it only worked when there was one electron. When there's more than one electron, they start to kind of interact with each other, which throws everything off because they are waves and can diffract, right? And it's weird to think about electrons as a wave. So I get that. It's a whole different, what we call paradigm shift. It's a different way of thinking about the atom. But that's how Schrodinger came up with his model. He treated electrons as waves, and we call this the quantum mechanical model of the atom. It's also sometimes called the Schrodinger model. And so Schrodinger's model applied equally well to elements other than hydrogen, unlike Bohr's model. And like Bohr, right, we said only worked for hydrogen. Like I said before, it's because he was treating them as particles, not as waves. When we treat them as waves, they can interact. And so they don't behave like they do in the Bohr model. This now explained the emission spectrum of all of the elements, which was cool because, again, when we were looking at the Bohr model, it only explained the emission spectrum for hydrogen. That was actually how they realized that the Bohr model can't be right because it didn't explain all of these colors we were seeing for the other elements. It worked just great for hydrogen. We could explain all of those different lines. But as soon as we started looking at other atoms, it didn't anymore. So the quantum mechanical model makes no attempt to predict the path of an electron around the nucleus. They're not trying to say anything about where it's going. So, right, whereas we had the Bohr model, right, and the Bohr model relied on these orbits, right? That's why we called it the planetary model. We said that electrons reside on these orbits and go around the nucleus like electrons orbit the nucleus like planets orbit the sun, right? This was called the planetary model. So we're not doing this anymore. Instead, the quantum mechanical model talks about areas where electrons might be, and we call these orbitals. Even though we use the term orbitals to describe things in the Bohr model, but the term actually came from this quantum mechanical model. We just kind of use them interchangeably now because we know more about what the electrons are doing. So orbitals are different from those orbits. So these we're going to call orbitals that you see here, and the orbits are like from the Bohr model. And so the reason that orbitals are different, they represent probability maps that shows a statistical distribution where the electron is likely to be found. So here on the right, that shows all the different places the electron could be or is most likely to be. So what they do is they take a circle, right? This is an s orbital. So they take a circle and they say, okay, within this circle here, we are 90% sure that the electron will be somewhere in there. Not 100% sure, but it's likely that it will be somewhere in that area. Okay, so this is how they're getting. So when we talk about orbitals, it's a region of space where the electron is likely to be found. So atomic orbitals, region in space in which there is a high probability of finding an electron. Not necessarily that we will find it, but that it's really likely that we will. So the way that we describe these orbitals is we use quantum numbers, and they specify the properties of each of these orbitals and the electrons that are within them. So we're going to talk now about the quantum numbers. So again, quantum numbers are describing the orbitals. So we have 4 quantum numbers. We're going to talk about each one. The first one is the principal quantum number, and that is represented by the letter N. Then we have the orbital quantum number, and that's going to talk about more of the shape of the electron. That will be represented by the letter L. We have the magnetic quantum number, which has more to do about the orbitals, and so this is ML. It's going to talk about the orientation. And then we have a spin quantum number, and this is going to talk about how the electrons are spinning. There are 2 electrons that can go in each orbital, and we have to have a way to distinguish between them. So some of them are going to be spin up and the others are going to be spin down, and we're going to talk about them shortly. But the way that we describe this is either MS, or sometimes they just use S. Either one is fine. These are the 4 quantum numbers, and they describe what the electrons are doing in each one of these particular orbitals. So the first one is the principal quantum number. This is what you think about when you think about energy levels. So if you've written electron configurations before, like 1s2, 2s2, 2p6, right? It's that number in the front, that 1s, 2s, 2p, and that indicates the main energy levels. And it's always going to be a number, 1, 2, 3, 4, and so on and so forth. This tells you the distance from the nucleus. Lower numbers will correlate to closer to the nucleus. Bigger numbers are farther out. And each main energy level has these sublevels that we're going to talk about. But like I said, low numbers means close to the nucleus. Okay. And so the maximum number of electrons that can go in each of these energy levels is given by this equation 2n plus 2. So like in the first energy level, we can say, okay, so if we're thinking about the first energy level, we would say the number of electrons in there would be 2 times 1 squared, which gets us 2. In the second energy level, it's 2 times 2 squared, right? 2 squared is 4 times 2 will give us 8. You can do it, for the third energy level, right? So we have 3 squared, so 3 squared is 9 times 2 gives us 18, and so forth. So that's how many electrons can go in each one of these energy levels. The orbital quantum number is also sometimes called the angular momentum quantum number. So when you get into higher levels of chemistry and physics, they'll call this the angular momentum quantum number. But for now, we can just call it the orbital quantum number. It's telling you the shape of the orbitals. And this is denoted by L. So these are cursive L's. I know they look a little bit weird in the script, but they're always going to be n minus 1. Okay, so if we have, in the first energy level, we can only have S, right? So if we think about the first energy level, we go 1 minus 1, that gets us 0. So in the first energy level, there is only the S orbital. In the second energy level, we can go, 2 minus 1. So that gets us 1, which means that you can have S and P. So you can have, whatever this comes out to, you can have this and the stuff below it. Whereas the first energy level, right, can only have S. Third energy level, 3 minus 1, that gets us 2. So that means we can have, S and P and D now. So you can have whatever that, L comes out to be and anything below that, any lower numbers. So that's how we're figuring out the angular momentum quantum number. And so these SPDF, if you're not familiar with those are describing shapes of the orbitals. So I'm going to show you what they look like. This is an S orbital. S stands for spherical. So they are making spheres around the nucleus. The 1s is closest to the nucleus, and so it's going to be fairly small. which is why this little tiny guy, right, those are the 1s electrons, are going to be super close to the nucleus. And so this, I don't know where the label went, but that's 2s, right? So it's a little bit bigger, it's a little bit farther from the nucleus. And then down there at the bottom, we've got the 3s, which is larger. Okay, so all s orbitals are spherical, and their size increases with the increasing principal quantum number. So as the number in the front gets bigger, the s orbital gets bigger because it's encompassing more and more space because it's getting farther and farther from the nucleus. So here is what an s orbital would look like, right? This is that like probability map that we were talking about earlier. Okay, and so this graph, right, that's labeled B here, it says the probability of electron being at a point, and that's, right, this is psi squared. And that's that probability, right? So anytime you see that symbol, that's talking about probability. So as we get really close, right? So if this is 0, right? This is distance from the nucleus on the bottom. When we're really, really close to the nucleus, there is a high probability of finding an electron. And as we get farther and farther and farther from the nucleus, right, there is a lower chance of finding the electron. And if we look at this picture right here, that's why the dots are really dense close to the nucleus. There's a really good chance that the electron is going to hang out really, really close to the nucleus. And as we get farther and farther and farther out, right, the dots get farther apart, which tells you that there are, it's a lower probability of finding the electron out there. So if we think about these rings, right, you can think about saying how likely is it to find it in the first ring or the second ring, right? And that's what it's talking about, this radial distribution here. If you'll look, they added a little bit here to this, right? Because the electron is not going to hang out super, super close to the nucleus. It's actually going to be most likely to be a little bit apart from it, not quite on top of it. But again, you don't really need to worry about that so much. And why that happens to be. What you need to know is that essentially, as you get farther from the nucleus, it's less likely that you would find it. So here's what our s orbital looks like, just in general. And so, like we said, it's likely to be really close somewhere in here, less likely to be somewhere out here. So if we think about the 2s orbital, the 2s orbital has two different regions of high electron probability, and both of these are spherical. So if we look at the 2s, the 2s, right, the region near the nucleus is separated from the outer region by a spherical node. So this is this node here, right, where there's not a lot of electrons that are hanging out there. Okay, and so the electron probability in that node is essentially 0. So if we're thinking about this 2s, right, because the 2s is encompassing the 1s, so it's really likely to find the electron, fairly close to the nucleus. That would be that 1s, those 1s orbitals. Then there's going to be this node, and then this more represents like the 2s, where the electron is also likely to be. This guy you don't really need to worry about so much. But essentially what you're looking at is the electron will be somewhere in here, right? Or it will be somewhere out here. And it's not going to be on this node in between. So now we're moving on to p orbitals. There are 3 p orbitals. So all p orbitals are what we call dumbbell shaped. So the three p orbitals are oriented along each one of the axes. So if you look, this one is p sub x, this first one, and it's oriented along the x-axis. And then we have p sub y, which is oriented along the y-axis, and then p sub z, which is going up and down on that z-axis. And if you combine them all together, this is what all 3 p orbitals look like together. Essentially what I want you to know is that there are 3 p orbitals, and they are dumbbell shaped. I'm not going to ask you to draw these. I am terrible at drawing, and I just assume that all chemists or anyone in chemistry is terrible at drawing too. I know that's not necessarily true, but I'm not going to ask you to draw these, but I would expect you to maybe recognize that this is a p orbital, like if I showed you a picture. There are 5 d orbitals. Okay, and they each have similar shape, and then they lie in the same plane. The last one's a little bit different. So here's what they are. So there's 4 of them that look similar, and then one that's not. But we call these double dumbbells. So there are, the f orbitals, or sorry, the d orbitals are double dumbbells. So we have dxy, which is in the xy plane, dxz, which is in that xz plane, dyz, which is in the yz plane, and then we have this one, dx squared minus y squared, which is still essentially kind of in the xy plane, just oriented a little different. And then this one, so I remember this as 4 double dumbbells, right? 4 double dumbbells, and then a dumbbell with a donut, which I know sounds a little bit silly, but that's how I remember this last one. So it's 4 double dumbbells and a dumbbell with a donut. And so then when you combine them all together, you get this. What I want you to know for this is that you have 5 d orbitals, and that you could recognize the double dumbbells or the dumbbell with a donut. Again, I'm not going to make you draw these. I can't draw. I just assume no one else can either. And then these are the f orbitals. So there are 7 f orbitals, and they all look a little weird. So however you want to, learn these, I figured out that, if it's not an S, a P, or D, then it's an F orbital, and they look just kind of bizarre. Again, not going to ask you to draw any of these 7 F orbitals, but there are 7. Okay, so these are all the different shapes of the orbitals. So I want to just write, let's see if I can just write you like a summary here. Nope. No, going back too far. Okay, never mind. I'm just going to... Sorry, give me a minute. I'll just click back through again. If I click too fast, it zooms. Sorry, everyone. All right, so here, this was on the last slide. So in the, we have SPDF. So I remember this in order by saying SPDF. And me saying SPDF is odd, right? SPDF is not a word. That's odd that I would say that. You guys know I say odd things sometimes though. So the number of the orbitals then is odd because SPDF is odd. So in the S, there is one S orbital. P has 3 orbitals. D has 5 orbitals, and F has 7. So I just remember SPDF is odd. And so then I will always remember how many orbitals go for each of those. So the way that we describe each of these orbitals, right, because there were 3 p orbitals and 5 d orbitals, and we have to have ways of distinguishing between each one of those orbitals. So the magnetic quantum number indicates the orientation of the orbital in space. So it's telling you essentially which one of these p orbitals or d orbitals we're looking at. Is it going along the xy axis? Is it going along the xz axis, right? So it's telling you how it's being arranged. So the values of m sub l, right, that's what this is, m sub l, are the integers negative L to positive L, right? So you figure out L from n, right? And then we can figure out our m sub L from L. So the number of values represent the number of orbitals. So here's an example. If we were going to say L equals 2, right? So an L equals 2 represents a d orbital, d sublevel, okay? And so if we think about SPDF, right? SPDF is odd, 1, 3, 5, 7. So we know there are 5 d orbitals. So if we think about, so this was L equals 2, right? And that corresponds to D. So there needs to be 5 sublevels. So M sub L is going to range from negative 2 to positive 2, right? Negative L to positive L. So we write out those numbers, negative 2, negative 1, 0, 1, 2. And if we count them all up, 1, 2, 3, 4, 5, that gets us our 5 D sublevels, okay? So that's what that is. So when it says from negative L to positive L, you're just going to write out the numbers, from negative to positive, and that's going to tell you all of the orbitals that there are. But it should always add up to the number, right, from SPDF. So here's just kind of a general summary. So if we have our n equals 1, right, so n equals 1, our L can only be 0, right, because L is n minus 1. So 1 minus 1 gets us 0. So if we're thinking about our m sub L, negative 0 to positive 0 really just gets us 0, which is fine because, again, SPDF, right, we should only have one s orbital. For n equals 2, right, we get our L. So L is going to be n minus 1. So 2 minus 1 gets us 1. So we can have 1 and 0. Remember, it's always going to also include ones below that. So for L equals 0, right, we have m sub L, and we have, which is 0. So we have a 2s, and we will also have 3 2p's. So it'll go from negative 1 to positive 1. So negative 1, 0, 1, and which is great because p's should have 3 orbitals. And so on and so forth. D's will have 5, F's will have 7. Okay, so this is just a good kind of summary / example slide. Our last quantum number is m sub s, or sometimes just s, and it describes the electron spin, okay, which is a weird thing to think about. And we do it just to denote between the two electrons that can exist in an orbital. So electron spin quantum numbers explain some of the finer features of the atomic emission spectrum. We're not going to get into those. You can get into those in higher levels of chem. But essentially, if you've drawn orbital diagrams and things like that, you might be familiar with this, where we always draw one of the electrons going up, right? Each of those arrows represents an electron. We draw one of them going up and one of them going down because there are 2 electrons that can fit in an orbital. And we're going to talk more about this in the next chapter, but 2 electrons can go into each one of those orbitals. So one of them, and they can't have essentially the same address. They can't have the same set of quantum numbers. So we show one of them going up and one of them going down so that they have different, so that they're different. And the way that we denote between them is that we'll give them, oh, sorry, that's kind of small. This here says plus 1/2 or minus 1/2. And we're going to say that one of them is spin up, which would be this guy, right? This would be plus 1/2. And the other one is spin down, we say minus 1/2. And this whole spin that I'm referring to is the magnetic field induced by the moving electron charge of the electron as it spins. So remember, way back at the beginning of chapter 7, I was talking about when energy is moving, right? When electric charge is moving, then it's always going to create a magnetic field that is, perpendicular to it. So at 90 degrees. So it will create, right? These moving electrons are creating a magnetic field at 90 degrees from the direction of moving. So it's telling you whether the magnetic field is essentially, is it going up or is it going down? Again, I'm not going to make you draw any of this, but I would expect you, to understand this, especially as we move forward and talk more about electron configurations. So you only have 2 options for m sub s, right? You can either put plus 1/2 or minus 1/2. Cannot put any other numbers. You can't put 0, you can't put 1. The only 2 things you can write are plus 1/2 and minus 1/2, and that is all. So it's not like all the other things where they can vary. Your options are only those 2 things, plus 1/2 or minus 1/2. So here's an example how this might show up. So it says, list the values of the 4 quantum numbers for orbitals in the 3D sublevel. Okay, so think about this. This number in the front tells us our principal quantum number. That is the value for n. Okay, so n equals 3 because the number in the front is 3. And the way we figure out L, right, L is always n minus 1. So we have 3 minus 1, which gets us 2. So that's telling us L is 2. Okay, so now L is 2, which is good, right? That correlates to the D sublevel. Okay, so D is L equals 2. And then remember that M sub L always varies from negative L to positive L. Okay, which means M sub L is going to go from negative 2 to positive 2. So it's going to go negative 2, 1, negative 1, 0, 1, 2. Those are going to be our values for M sub L. And then again, you only have 2 options for M sub S, and you're always just going to write both of them. So you're going to write plus 1/2 and minus 1/2 every single time. So this is not going to change. Okay, this is going to be the same for every set that you're writing. Okay, the top 3 can change. That one is not going to change. Anyways, that is the end of chapter 7. I know it's been a lot just of new information. Chapter 7 is really tricky, and like I said, there's an entire course on this if you go into higher levels of chem, and everyone struggles with this chapter. This is probably the hardest chapter to cognitively understand in the course just because it's kind of abstract. I would recommend read your textbook, really work through some of these problems, watch the videos that I've posted, do your best to understand this stuff, and as always, ask me any questions that you have as they come up. Otherwise, it's the end of chapter 7. Make sure to do those ALEKS assignments. Like I said before, there's one that's due on March 21st if you've been working ahead. That probably is passed by now. But the other one is due March 25th. So make sure you do those. Thanks.